Okay, hi everyone. Thank you for coming. I'm Euan, and I work on Swift services and infrastructure at Apple. And what that means is I often find myself building Swift programs and putting them in container images. And now I'm into a little package called Swift Container Plugin, which tries to make that process a little bit smoother. And today I'd like to take you on a tour of the basement of the container world. We're going to wander through some dusty corridors and look at the foundations that people don't often visit. And hopefully see that bringing containers and language tools together can streamline your workflow in Swift or indeed in any other language. But let's start up in the fresh air. We're now living in the cloud-native era, and that's changed how we run our services and also how we build and deploy them. So let's say that I'm ready to deploy a service into the cloud. It used to be that I would compile a binary and FTP that onto a server, and I was done. That was it. But that's no good anymore because my cloud provider runs containers, and a binary on its own isn't enough. What that means in practice is that I need to package my binary in a container image. I bundle it up with all the things it's going to need at runtime. And then once I have my image, I can upload it, publish it to a container registry, which is an image store in the cloud. You've heard of Docker Hub, but your cloud provider probably runs its own registry, or you can host one yourself. And the beauty of publishing a container image is that once it's in the registry, I can deploy it to any container-based platform I like, whether that's a public cloud or in a private data center. My service has everything it needs in its container, and so it can run anywhere. And that's really revolutionized how we do deployments. It's taken away a lot of the problems that we used to face in setting up services and moving them around from place to place. But what particularly interests me is how container images get built in the first place. Because that's the part I deal with on a daily basis. Containers are now a big part of my development cycle, or let's face it, it's really more of a debug cycle. Whenever I want to test my service, I need to build a container image and deploy it somewhere. And I need to do that over and over and over and over and over again. The way I see it, in this cloud-native era, the container image is now my final product, just as much as an ELF file or a macOS executable might have been in the past. But the conventional way that you build a container image when you use a container runtime kind of turns that workflow inside out. It's another tool which wraps the whole build process. What I'd really like, since this is my final product, is for the familiar development tools that I'm already using to be able to build a container image for me. And so instead of bringing Swift into the world of containers, how about bringing containers into the world of Swift? Now, Swift might be new territory for some of you, so before we switch on our torches and head down into the basement, let's take a quick look at that. If you have an iPhone or a Mac, you've probably run an app written in Swift today. But you might not have realized it, but some of the cloud services that you've been using may also have been Swift-based. Because it turns out that the qualities that make Swift a great language for application development also make it ideal for large-scale services. And it's a very flexible language. It's now making its way into embedded systems as well. Swift was introduced in 2014, and it became an open source project under the Apache license the following year. So it has all the features that you'd expect in a modern programming language, with a strong focus on safety, efficiency, and interoperability. One of the first things that you'll notice when you start writing Swift is that it's very expressive. You can get lots of things done without a lot of ceremony. And it has a rich type system, which will help you to catch bugs at compile time. But it also has type inference, so you don't always have to write the type annotations by hand to take advantage of that checking. It's efficient at runtime, too. The Swift compiler is based on LLVM, so it builds highly optimized native executables for a variety of processor architectures and operating systems. And bear that in mind, it'll be important in a minute. Swift is memory safe by default, of course. You can't accidentally use uninitialized or deallocated memory, although there are escape hatches if you need them. And instead of a garbage collector, it uses automatic reference counting to manage memory with low runtime overhead. Interoperability, as I mentioned, was a goal from the very beginning. The first platforms where Swift was used already had lots of powerful frameworks written in languages like C, C++, and Objective-C. And so Swift was designed to make it as easy as possible to reuse those existing libraries. Now, if you've tried this in another language, you probably know that using a foreign function interface can be a bit risky, because you lose many of the safety features of your nice modern language. But with a bit of annotation, you can teach Swift about things like a library's allocation rules and object life cycles, and not back into many of its protections, which will help you to use the foreign library safely, even though the underlying implementation is still in a less safe language. Doug Greger spoke about this in depth at FOSDEM this year, and I'd highly recommend you take a look at his talk. And then Swift also has first-rate support for concurrency, which is critical for the kind of high-performance network services that we're trying to build. Again, there's that focus on efficiency and safety. Swift encourages you to use immutable copy and write value types instead of shared data, and that helps it to provide strong data race guarantees. And then to make sure that to make concurrent code as pleasant to write as well as fast to run, it supports asynchronous functions, that async await style that you may have seen in other languages. So you can write non-blocking network code in a straightforward, natural style instead of getting tangled up in callbacks. One final modern language feature, which is going to be really important for us today, is a tightly integrated build system and package manager. So Swift Package Manager understands the structure of your Swift project and knows how to take care of fetching your dependencies and building your targets for you. And it also has a few tricks up its sleeve, which lets it stretch into other areas, such as building container images. But don't worry, I'm not a member of the Magic Circle, so I'm not sworn to secrecy, and I can let you in on all the details. So let's take a look. Okay. So we're going to build and deploy a little web service. It's written in a popular open source web framework for Swift called Hummingbird. And there's not a lot to it. We start by creating a request router. And it's going to handle one route using this handler. The handler is defined in a closure, which is like a block or a lambda. And inside the closure, we produce this very sophisticated response that we're going to send back to our client. With our handler created, we set up an application server, wrapping it, and then down here, we start it running. Now this function call will run forever. The only way that it'll exit is if we throw an exception. We're not doing anything to handle the exception, it'll just bubble up. So this isn't exactly production-ready code, but it'll do for now. Oops. Okay, so that's the code for our service. What else have we got in here? Well, we have the rules for building it, which in Swift come from a file called package.swift. So far, so this is equivalent to the Go mod file or a Maven project or something like that. So far, for this little project, we don't have much in here. We just have a dependency on Hummingbird. We also have a dependency on Swift Container Plugin because it's distributed as a Swift package. And then we have the binary, the target we're trying to build. One thing you might expect to see here is a container file. You might call it a Docker file or a Podman file or something like that. But where we're going, we won't need one because Swift Package Manager will be able to build the container itself using the Swift Container Plugin. And so we can get started on that now. So I'll get it running. Now, the plugin is asking for network permission because on macOS, plugins run in a very constrained sandbox. So you have to ask for network permission so that the plugin can push the image it's going to build across the network to the registry. So it's done its work, built in a container, and given us a reference to it. So I'm running a local container registry here just because I didn't want to be depending too much on the Wi-Fi. But if you were to push to a cloud registry or to a registry somewhere else on the network, it would look very similar. And this is a completely standard Linux-based container image that we've built. And so we can run it on any of our choice of compatible container runtimes. But as it happens, a couple of weeks ago, Apple introduced a new container runtime specifically designed to run Linux containers really efficiently on macOS. So why don't we try that one? So it's called Container, and I've copied my reference. I give it to the container, let it run, and there's our little Hummingbird service up and waiting for us to contact it. Now, the container runtime, one of the special things about it is that it runs each instance in its own micro virtual machine, very lightweight virtual machine. And that means that each instance has its own connection to the virtual network. So we need to find out where it's listening. And there it is. We should be able to curl it. And there it is. But as I mentioned, these are completely standard Linux-based container images. And you might develop on your laptop and then deploy to the cloud onto one of the many cloud providers that accept containers, or you might put it onto your own private cloud. I'm, again, not going to be pushing to the cloud here, but I can run it on a different runtime here on my laptop. So if I start up Podman, it starts up. And Podman exposes network services using port forwarding, so this one will be listening on localhost. But if you can see down the bottom there, we've now got the same container image, just running on a different container runtime. So that's great, but I think we could make it a bit more topical. So why don't I make a little change? OK. So now we have to go back round that release debug cycle. So let's see if we can make that happen. This time round, I'll use a flag called allow network connections, which will mean that we won't be prompted to give network access. So that's fine. And then in order to avoid having to find out where the service is listening, it would be nice to give it a DNS name. Container has a built-in DNS server, and I've already set it up to serve the .test domain on my laptop. And so if I give my container a name using this flag, then it will be available under hello.test. And we can put those two things together. It's a slightly long command line, but it breaks up quite logically. This is our Swift package build, and this bit within the dollar brackets. Dollar bracket is a command substitution, so what will happen is this Swift package command will run. It will build our container, and it will print the container image reference onto standard output. And then the shell will take that and substitute it into the container run command, just as if we typed it there to begin with. And so in one command, we will build, push, and deploy our container. And this idea was inspired by a tool called Go from the Go ecosystem, which allows you to build containers around Go programs. So I'll get that running. And so Swift Package Manager is rebuilding at the minute. There we go. Then the plugin will start wrapping the image up. And then after that, we saw starting container. So now we should be able to find our service under hello test, and that's a lot better. So we had to pull off a couple of tricks to build those images, and they're both in this single command. Again, I promise you it's a single command. It's just been line wrapped. The first trick is to build the server binary. And that doesn't sound so difficult, but remember I'm running on macOS, and yet we produced a container that we would deploy on Linux. So somewhere along the way, we built a Linux binary to put in it, and that's a little more unexpected. And the second trick was to build the container image itself. And we did that from first principles. We're not shelling out to other tools behind the scenes here. These are completely organic, free-range container images. So let's see how that was done, and we'll start with the server binary. So the conventional way to build a container image, as I mentioned at the start, is to use a container runtime on your laptop. And it's not always obvious, but even if, like me, you're running macOS locally, when you build a container image using a runtime, you are actually compiling your binary on Linux itself. Behind the scenes, your container runtime will start up a Linux virtual machine. It will read in the container build recipe, that file we didn't need earlier on with the plugin, and it will start up a container build inside the VM. It'll copy in your code, and then inside there, it will run the full Linux version of the Swift compiler in a Linux environment, and that's how it's able to build the Linux binary that it put in the container. But there is another way that we could build that Linux binary using the native Swift compiler that we already have on macOS. And that's because Swift has always been great for cross-compilation. The Swift compiler is based on LLVM, And so it can compile for lots of other platforms. But a cross-compiler isn't quite enough on its own, because to produce a viable binary, you need to be able to link those object files against libraries and runtime files for the target system. And that's where Swift SDKs come in. They provide those supporting files that we need to cross-compile to Linux and even to different processor architectures using the open-sourced Swift toolchain. And cross-compilation is just as useful if you're running Linux. Maybe you have an x86 laptop, but you'd like to deploy on ARM in the cloud. Swift SDKs will let you do that too. Earlier on, we built the binary using the static Linux SDK from swift.org. And to do that, I installed the open-source Swift toolchain using Swiftly, which is a toolchain manager. And then I followed the instructions to install the static Linux SDK. So let's take a closer look at that. Over to here. Good. So like I mentioned, I've installed the static Linux SDK, and it requires the open source Swift toolchain, so I've got that as well. Before I start using that, though, let's just take a look at what an ordinary native Swift build looks like. So I've run Swift build. It's built this little test project, and it's produced a macOS executable which can run on macOS on this laptop. Great. What if I want to cross-compile to Linux? Well, all I need to do is to add this Swift SDK flag. That will tell Swift build to use the SDK I installed. I run the build. The output looks pretty much the same as the native build, but this time I've built an ARM Linux binary, an ELF binary, 64-bit, and it's statically linked. It's wrapped off the end of the screen. But it's statically linked against both the Swift runtime and the Muscle C library. Now, statically linked binaries are great for deployment because they don't require a lot of support at runtime. They bring all their dependencies with them. But exactly because of that, they also can be a little bit bigger than dynamically linked binaries. You might also want to build a dynamically linked binary because you want to use dynamically linked libraries that are provided by your Linux system but aren't available in the SDK you can get from swift.org. And whatever the reason, we've got you covered because there's another project called Swift SDK Generator, which is also open sourced on GitHub. And what it does is it allows you to build yourself a custom Swift SDK based on either the upstream container images for Swift or the upstream OS packages. And so you can build a custom dynamic linking SDK. Let's take a look at that. So earlier on, I installed it, or fetched it, and I ran this command, which generated me my new dynamic linked SDK. And what it did was it extracted just enough of the Swift runtime system for Linux to support the cross-compiler to allow it to build a Linux binary. And it produced a thing called an artifact bundle, which is the package that you can install into Swift Package Manager. And so if we look inside that thing, we should be able to see some familiar looking files. So I'll go down in there. This is the longest path in the world. I think this is what they mean when they talk about a deep dive. If we dive deeply enough into this artifact bundle, we start to find some familiar looking directory names and structures. And if I go one step further, we find some Swift files which will look familiar to you if you've done any Swift programming. So these Swift modules are informative files for the compiler that tell it things about the libraries and frameworks you have available. And for example, Foundation is one of the most widely used frameworks. I would say the majority of Swift programs out there use Foundation in one way or another. And if I just search, we can see it has some sublibraries, but when we go down a bit further, we see also the shared object file. This is the library that provides the object code for Foundation. And indeed, that file is an ELF library file. So this is all the supporting infrastructure that we need for the cross-compiler. And we can try to install that now and use it to do a build. So I'm installing it into Swift Package Manager, and I'll pop back up to my little test project. And now I should have an additional SDK in my list, and indeed there it is. And to run it, I use the Swift build flag again, but I use a slightly different name, ARch64 unknown Linux GNU. And if I run that, we have, again, a sort of completely unremarkable build output. Looks just like all the others. But this time round, we've built ourselves a dynamically linked Linux binary using that new SDK. So that's how to build the Linux binary using the Swift compiler we already have. The second trick is how to build the container image. But what is a container image, really? They're a bit of a mystery, I find, because they're usually managed behind the scenes. You know, you build a container image and you don't end up with a file like in your project directory. Stuff happens somewhere, but you don't see it. I kind of think they're a bit like the Yeti, or maybe I should say, maybe here I should say they're like Bigfoot. Because you see their footprints as they're pushed around. You see these strange hexadecimal numbers and progress bars and so forth, but you never see an image close up. Actually, it turns out images are pretty straightforward inside, possibly also like Bigfoot. And because they're an open standard, originally defined by Docker and then donated to the Linux Foundation, there are lots of tools that can work with them now. And we can equally well build our own tools in Swift or indeed in other languages. So inside the image, there's a tree of objects. And to keep it simple, I'm going to look only at a single architecture image, which starts with a thing called a manifest. The manifest points to some configuration, and that tells the container runtime how to run the image when it starts it up. It also points to a stack of layers, which combine to make up the container's file system. Now, all of these metadata objects are JSON, and the layers are tarballs. So this is a structure we can easily build for ourselves in Swift. But I often find the best way to understand something is to take it apart. Even better if I can put it back together again. So let's try and look at the insides of a container image. Come over to here. Good. So the registry is just an HTTP server. Hope you can read that. And what that means is that we can fetch a container image by hand using curl. You need to pass the accept header and so forth. There are a couple of details, but basically we ask the registry for the manifest, and here it is. So this is the manifest for the image we've been looking at. And the first thing we find in here is that configuration. And so I can fetch that as well. The registry treats all of these things as opaque blobs, but we know this is going to be JSON, so we can pass it through JQ to tidy it up a bit. And there you can see all that stuff that I was just telling you about. Here's all the information the container runtime could want to run this image. It's like, here are the environment variables it should set up. If I go down to the bottom, here's the list of layers that go into this image. And back up at the top, one of the important things is the entry point, which is what executable is supposed to run in this container when it's started up. The next thing we find in the manifest is the set of layers. Those, again, are just being treated as blobs. But this time we know these are tar balls, so we can untar them. And so this first layer here is the generic Linux image that underpins this whole container image. You can see lots of Linuxy stuff, configuration files, and etc. This is clearly an image which is based on Ubuntu. And if I go down further, we start to find all those binaries that you'd expect to see on a Linux system. So this is the generic Linux base image. The next layer isn't terribly interesting. What it does is it adds the TLS trust roots that this image will use at runtime. So it just adds a bunch of files. But the third layer is important for us, because this is the layer that adds the Swift runtime system. And these are the same names we were just looking at a moment ago in the SDK. So yeah, Swift module files. If I look for foundation, there's this foundation Swift module, a whole bunch of submodules of it, and then a bit more. And then here we have the shared objects that our binary is going to depend on at runtime. So this is the layer that takes a generic base Linux image and turns it into a Swift base image. So all we really need to do now is pop our binary on top, and that's what happens in the last layer. So there it is. There's our hello world stacked on top. Okay, so, oops, I should zip out of that and get back to my slides. So that's how to take an image apart. You start at the manifest, you follow the pointers to download the configuration and all the layers. You unpack them, and then if you're a runtime, you run whatever entry point you were told to run. What about putting it back together again? Well, we just have to retrace our steps. Let's say we built a new version of our service, and we want to package it on top of the same base image. Well, we need to replace a few pieces. We can reuse the base layers, that's the whole point, but we need to wrap the executable in a new layer. And then we'll need a new image configuration, which will have new environment variables, new entry point, that sort of thing, references to this new layer. But that's still not an image we can actually pull. When we started downloading this thing, we started at the manifest. And so it makes sense that in order to make a new image, we'll need to make a new manifest, stitching everything together, the new configuration, the existing base image layers, and the new application layer. So let's have a go at that. Okay, so earlier on, I prepared a new service binary using that dynamic SDK that I generated. So to make a new image out of that, the first thing I need to do is to make a layer for the application. And we know that's just a tarball, so that's pretty easy. Next thing is to build a new configuration. And so this is a simplified version of the configuration from the Swift Slim image. I've just removed some of the things that are a bit distracting. The essentials here are we need to add our new layer. So I will do that. And we need to know the hash. So that's there. And then while I'm here, I should change the entry point. Just so that when this layer starts up, it will run our new service. And so now I'm pretty much ready to start uploading things to the registry. We can assume that the base image layers are already there, because we know they are. A real implementation of a tool like this would check, but there's a demo, so we'll cut some corners. What I will do before I upload, though, is I will gzip the application layer. It's not mandatory, but most file system layers get zipped before they're uploaded. And the upload process itself can be a little bit tricky, so I'm cheating slightly, and I've written a little script. To upload a blob to the container registry, typically you need to make at least 2 HTTP calls. The first call, you ask the registry to open you an upload session. And it will return a location URL with a bunch of encoded parameters and other stuff. And then the next thing you have to do is to make at least one more HTTP request to upload the contents of your blob to that location URL. So there are a bunch of details to keep track of here, and this script is just making sure that we don't have any finger trouble. So let's use it to upload the application layer. And then because we saw that the config is just another blob, we can do the same thing for the config. Okie doke. We still don't quite have our pullable image, though the last thing we have to do is the manifest. So we've changed the config. So let's update the details of that. And we've added a new layer. So I'll just copy this existing layer and fix the details for it as well. Now, if you're eagle-eyed, you'll have noticed that in the manifest, we're using the digest of the compressed blob that we've uploaded to the registry, whereas in the config, we used the digest of the uncompressed contents of that blob. That is a detail of the way that this distribution system works that always catches me out, but hopefully if you ever try this, you'll be prepared and it won't catch you out. But the manifest also isn't treated as just a blob. There's a special URL for it, so we can make a curl request to upload it. And we're going to give it the tag handmade. And so now all we really have to do is, the moment of truth, is to try and pull it. And it's pulling, that's a good sign, and it's starting up. So we should be able to access it. And there we go. So if you really find yourself in a tight spot, all you have is curl, maybe some chewing gum and a paper clip, you can create yourself a container image by hand. But it was a bit tricky. Thankfully, the container plugin comes with a little helper tool which deals with all these, keeps track of all those details for us. So I'll just cd in there and run it. So you might have noticed some of this output going past before. This is the tool which is used by the plugin to do the work. And all it's doing is the stuff that we just saw. It's finding a manifest, finding the configuration, building an application layer around it, uploading it. It is a responsible citizen, so it actually checks that the base images exist. And then when it's finished, it tells us where to find the image that it uploaded. OK. So now you really have seen all the tricks. We built a Linux binary by cross-compilation, and then we packaged it in a container image. But we want that to happen every time that we are going to rebuild our services. And so the last part is to automate it using a Swift Package Manager plugin, which will work behind the scenes to sort of tie all these steps together. Plugins let us extend Swift Package Manager to suit our own requirements, adding our own commands and build steps, which look just like built-in features. When we ran this Swift Package command, for example, Swift Package Manager started up, and it spawned our plugin, passing it a set of plugin arguments. And the plugin then called back to Swift Package Manager and said, please build the Hello World target, which it did using the SDK that we'd chosen. That produced our Linux binary, which the plugin then wrapped in a container image using container tool, uploaded to the registry, and then finally returned back the image reference, printed it on the command line, ready for us to pass into the next command. OK, so we've had quite a lot of fun with our poor, long-suffering container images. We've taken one apart, we've stuck it back together again with crazy glue, and we've extended Swift Package Manager to do all of that for us. I think it's fascinating that the container image format is so simple that you can literally create one by hand using curl and vi. And yet it's so flexible that it underpins the whole modern cloud-native world. But as much as I'm fascinated by how they're built, a container image which just sits there on a dusty shelf in the registry is a bit sad, because containers are built to be run, whether that's on your laptop or on a server somewhere in the cloud. And today we've been using the container command to run our images mostly. It's an open source desktop container runtime, which was specifically designed to run standard Linux container images on macOS. And it was also written in Swift, and we just have time to take a look inside. So container is built with security and efficiency in mind. Every instance runs in its own lightweight virtual machine and has its own connection to the virtual network, as we saw. Each has its own IP address. So what that means is your host machine and your container workloads are isolated and protected from each other by the native macOS virtualization framework. And that's great for security and privacy, but it's also good for efficiency, because when you stop a container, its virtual machine is shut down as well. There isn't a persistent, long-running VM in the background. And so if you're not running any containers, you're not running any VMs either. And the resource use goes almost to nothing. It even tears down the virtual network bridge when it's not being needed. But the container CLI is just the tip of the iceberg. It's built on a Swift framework called containerization, which in turn builds on top of the built-in macOS virtualization framework and provides primitives for dealing with container images and file systems and networks and all that sort of stuff. Container takes those primitives and stitches them together to create a fully fledged desktop container runtime with a familiar command line interface. But the containerization framework is also open source, and you can fetch it from GitHub and use it to bring containers into your own projects as well. So how does containerization actually run a container? Well, we're dealing with standard Linux-based containers. So the first thing that we need in our little VM is a kernel. And the container runtime command will fetch one when it's installed. Next, we need an init system, which will start up the container and monitor it while it runs. Containerization includes a lightweight init system called vminitd, which was also written in Swift. And in fact, it was cross-compiled using the same static Linux SDK that we used earlier on to build our examples. And the great thing about vminitd is it provides everything that's necessary to manage a container's lifecycle inside the VM, but nothing more. And that's part of why container instances are so efficient and they start up so quickly. Finally, we need to fetch our services container image. But we can't use it straight away. Just like when we were downloading the images by hand with curl, containerization needs to unpack the image. It goes through layer by layer, unpacking the service executable and all of its supporting libraries. And it builds up a root file system image, which it then mounts into the virtual machine, which is going to end up running the container. Now, after all these Linux builds, I can forgive you if you've forgotten that we can also actually build macOS programs with Swift. Crazy idea, right? But so for a little bit of change of scenery, let's hop into Xcode for a quick sort of lightning tour of the highlights of the containerization framework. Okay, so containerization is under heavy development at the moment. And so some of these APIs, the details of them will change, new things will come, things will change. But the landmarks, the major landmarks, should still be something you can recognize. We'll also cut a couple of corners in this example just to keep everything simple. So if you want to see how to do this properly, you should check the code for container itself or the cctl command in the containerization repository, and you'll find both of those on GitHub. But with that said, let's start. The first thing we know is that we're going to need to deal with container images. So we need somewhere to store them. And so we create ourselves a local content store object. And then we are going to need a Linux kernel. So I have a copy of the kernel which the container tool also uses, which I've set aside for this project. Next thing is we need to fetch that init system. And as it happens, the init system, VM initd, is distributed as a container image itself. It's container images all the way down here. And so we can ask our image store to fetch it for us. We can't use it directly, so the next thing after it's fetched is we have to turn it into a boot file system, which we can mount onto our VM. We do the same for the container image that we actually want to run. It's going to be another of our hello worlds. So we ask the image store to fetch it, we unpack it, turn it into a root file system. That's all the downloading that we need to do. Now we just need to build an environment where we can run the container. And because containerization is based on the built-in virtualization framework, the first thing we need to do is to create a VM. And that's just one function call. We give it the kernel and the boot file system. Then we wrap it in a container, Linux container object from the containerization framework. You can tweak the CPU and memory allocation and all kinds of things. I'm not going to do that here. But one thing I am going to do is attach a terminal, because we quite like to see what's going on inside this container. This is a bit of a corner cut. A real implementation would have to handle SIGWinch, which is the signal that tells you that your terminal size has changed. So what I'm going to propose is, let's just not change the size of the terminal, and don't tell anyone else. We'll keep it our secret. But an area where we can't afford to cut any corners is networking, because a web service without a network is kind of useless. So what we need to do is, first of all, create a network bridge, and that will come with a subnet. Then we want to make sure we can allocate IP addresses from that. We'll need to give one to each VM we want to create on this bridge. With that in hand, we can actually create a network interface, and we can attach it to our container VM. I have a couple of extensions to help with that. Because in order to make this work, we have to call a couple of new API calls in the virtual network code in macOS 26. And they deal in a much lower level representation of things than the containerization framework. So this function makes those couple of calls. But then this extension here translates the low-level representation of a subnet that the virtual bridge gives you into a CIDR address, which is a higher-level structure that containerization uses. I've got a couple more extensions here. Here's where we create our IPAM object, our address allocator, to make sure we don't accidentally give the same address to two containers. And then finally, we add another constructor to the network interface type to use all of those things that we've made to create an interface. This idea of using extensions, if you've not done any Swift before, it's really powerful and very commonly used. It allows you to add new methods or computed properties to types that you don't even own. I mean, framework types from the operating system, from anywhere. And it allows you to adapt them to fit more closely with what you're trying to do in your program. So it's a very powerful technique. So now all we have to do is start up our container. That's my cue to press play. and wait for it to start up and run. So we can see we've got our kernel, we've fetched our application image, the thing's started up, and it's listening on this IP address. So we should be able to curl it, and there we go. For one last time, hello, Denver. Back to the slides. OK, so now we really have seen the full container lifecycle. We've cross-compiled the Swift service for Linux. We've taught Swift's own package manager how to put it in a box. And then finally, we've used containerization, yet another Swift framework, to unpack the box and deploy our service. And I hope we've also maybe demystified a couple of things along the way. We've looked inside a container image, and we found that it's not really all that complicated. It's not a Yeti or a Bigfoot. It's just a bunch of tarballs standing on each other's shoulders in a trench coat. Is that any clearer? And although a container runtime is handling lots of details for you behind the scenes, it really just boils down to fetching some files from an HTTP server, unpacking them, and running an executable that you find inside. You can start using all of these tools today to build and run your container images. They're especially well suited for development. But I hope you've also seen that they're part of a toolkit, which you can expand and build on to create your own custom container tools and workflows. Or maybe you just want to say hello world with style. Whatever you want to do, to find out more, start at these GitHub links, or come and find one of us after the session. John and Aditya from the containerization team are here at the conference, although you might have to jog with them to the exit because they have really squeezed their travel plans quite alarmingly in order to be here, so thanks, guys. But yeah, we're really looking forward to seeing what you come up with these frameworks. Thank you very much for listening.